Well, first of all, I would like to thank you for inviting us to present this work that we've been doing on the Solar System Search Service that we've been developing within the ESASky team at the ESAC Science Data Center. We've been doing this work in close collaboration with Benoit Carey and Jérôme Berthier from the IMCC. So to give a bit of a background, well, why we decided to start developing this service. So first of all, we wanted to allow users to search through our entire astronomical archives for observations containing solar system objects, not only targeted, but also serendipitously. So obviously the main goal is to maximize the scientific exploitation of our data holdings. And for this first run, we tried to cover the full wavelength. So we included Hubble, Herschel, and XMM high-level metadata. For this, these are some examples from all collaborators using the results from our service. Max Malke presented at the ESA SSW11 at ESTEC. He did a study from our results on Hubble on the NEO population, and he was studying first of all, the signal to noise ratio of our detections. I will get into detail later and check how many targeted versus non-targeted observations were actually in the Hubble archive. This is one example, of one of the results he presented on this NEO 2000 H10, and this is the results from our service. So we are providing both the start position at the start of the observation and the end position in red at the end of the observation. This is the NEO. And he presented some other examples here as well from this another NEO 2006 SC349 with the ACS instrument. We also been working recently on the results that we are providing through the service to get an estimation on how many are really potentially detectable. So we've been doing some computing estimated the theoretical flux of these asteroids for each of the Herschel detections that we're providing, just to get a rough estimation on how many are observable. So we could provide that as well to the users, so they could go straight to these potential detections. And I'm providing here, this is CK, I will show you later as well through ESASky, some of the examples that we found of serendipitous detections. So that was Hermione. This is a targeted observation of Ceres, and you can see Sylvia here. It was just passing by. Also, we did recently, for XMM Newton, our service only included the EPIC camera, so that's the X-ray camera. But we did a specific study on asteroids in particular from all the results from our service. And for that, we included the optical monitor camera, which is covering from optical to ultraviolet wavelengths. And this is an example, I don't know if you can see it with this, sorry. This is an example of Barbara, one of these 900. We did the same study. In this case, we checked the limiting magnitude of each of the observations in the optical monitor and from the theoretical estimated magnitude for each of the detections. Well, we computed around, again, 900 potential detections. This is Barbara. As you can see here, our service is providing the start time position of the asteroid and the end time position for the entire high-level metadata, and that means of the full observation. So as you can see, there are several exposures, one of them subsequently. So you can see, we're predicting this path of Barbara through the entire observation, and well, you can see it moving around as the filters change. So, sorry, how we did this. Sorry, we created this SSO pipeline. It's written in Java and it's running in the grid, in the ESA grid to speed the computational time. So we are using as orbital parameters. The input is Astor, the asteroid dataset from Lowell Observatory, and the Comet Pro. And this is coming from the IMCC itself. So for the ephemeridess computation, we are using the IMCC E code, the eProc software version 3.2. And for this first step, we are sampling the orbit of the asteroids every 10 days for the time span that the spacecraft or the mission is flying. So in this case, as you can see, we have Hubble, Herschel, and XMM Newton spacecraft kernels. Some of them are provided for by external entities, and some of them we did them ourselves in-house. So while we're doing this evenly sample of the orbital of the path in the sky every 10 days, it's because we try to speed the process of selecting the potential detections for this. So what we're doing is we are basing this first step of the pipeline in this Hill Peaks sky tessellation that I think everyone is aware of that. So what we're doing is we compute the position of the SSO in the sky, and we compute all the cells that the solar system is passing through. And then we compute the cells that the footprint, this is a Herschel observation, so the footprint is falling under. And then we do a really fast cross match just to reduce the cardinality of the list. And then, once we've got like a short list, then we do the real cross match for this. Also, we're also using like a selection process to select the order of the cell that we're using. The bigger, the faster the asteroid is, the bigger the cells are, just to make sure we're not losing any potential detection. And the real cross match, once we've got this short list, then we recompute the position at the start time of the observation and at the end time of the observation. And then we do a geometrical cross match with the footprint itself. Well, there are several ways to access this service. The first one is the most usual one, is through the ESASky application, through the ESASky interface. So we've got this resolver of the asteroid. This is based on, again, an IMCC service. This is the SSOSS. And then we are providing, if we have any cross matches in our database, then we're providing users with this. This is the path in the sky of this particular asteroid, as seen by Herschel. And then this is one of the examples we're using in a recent article of CK itself. If I switch to the Herschel HIPS, you can see how CK detection is here falling right on the line. As you can see, this was a serendipitous observation. It was targeting another cloud. And this is an example of the metadata we are providing through the service. So all these metadata is related to the observation, and this is the metadata provided by our service itself. So again, the start time position, the end time position, some uncertainty on the position, and some theoretical parameters. There are more parameters. They could be accessed as well through TAP. So I had it open here, an example of one of the tables we are providing right now through the service. Sorry. So as you can see, as I was saying before, we are providing like a set of parameters at the start time of the observation, like position, Vmax, phase elongation, proper motion, and so on, and at the end time of the observation as well. Then we are providing what we call the cross-match type. This is basically to ease users to locate those detections that are really inside the field of view, for example, of the observation, and not, because we're also taking into account the uncertainty of the position. So there are several ways, several types of cross-match we call. And then in recent work we've been working on, we're also providing this flag of if it's visible, just to also, again, help users to find potential detections. So I think this was it. I'm not sure if I'm under my time, but just a final remark. So as I said, we developed this in collaboration with the IMCC as an SSO search service, and it's accessible through ESASky and allows fast discovery of observations from ESA missions. Right now, there are only 3. That potentially contains SSO within the field of view, both targeted and serendipitously. Well, we consider that the added value of this service that we are also providing not only one position, but also the direction of the expected detection. And a future work of that we are already considering is this orbital parameter input interface, because right now we are relying basically on both databases, data sets that I mentioned at the beginning, Asteroid and the Comet IMCC dataset. But we want to also allow users to just type in their own orbital parameters and we can run real live or dynamically. Also, there's some work on at the ESDC level on the data cross-area group on implementing this EPN tab protocol and to register in VESPA. And the first exercise is already been, well, it's in progress for the Herschel serendipitous observations I just shown you before. We also want to include what we've, this instrumental threshold, which means this limiting magnitude flux limit, all the work I've showed you at the beginning and we've been working on. And of course, include more missions like James Webb, again, in the data group I mentioned before. We already worked on a first prototype for James Webb future observations. So I think that's all I wanted to present.
Okay, thank you. That was, as usual, very impressive. Thank you. Any question